我今天给大家讲一下，就是我上次 demo 的时候讲了一个，就是关于 auto precompile 的，关于这个的一个相当于 benchmarking 的一些结果吧。然后那我就用英文讲，因为工作这样感觉比较方便一些。So before we talk about the benchmarking results for the auto precompile, maybe I'll just give a first like an overview of what is auto precompile, which I actually talked about like last week, but just as a like brief recap. So basically, for any ZKVM, you kind of start from a high-level language, and then to like an instruction set. But I'm just gonna start from the instruction set, like RISC-V, and then for each of the instruction, you're gonna basically replace that with a circuit for that instruction. So basically for a program, you have like a bunch of instructions. So kind of like this. And then each instruction gets like called by the CPU circuit, which like does a lookup to the circuit corresponding to the instruction. So you have like a CPU circuit where like each row corresponds to calling one instruction. And then given like the type of instruction being called, it does a lookup to like a chip. So say that this is the add chip, and this is the sub chip, the CPU circuit. Like these are the instructions. And then the same instruction like does the computation within the same chip. And then each of these generate a proof. And then there's the issue regarding the, like, without the auto part, that's the precompile. So some of the like calculation, for example, hash functions are extremely complicated. So instead of like saying a wechat function might have like 12,000 instructions, instead of doing like all of these one by one, which is very inefficient, we just replace that with a giant circuit, which is mostly handwritten. And that's going to be very accelerated, but with the disadvantage of you really need to like do that manually. Like each time you do you do a precompile without the auto part. So the idea of the auto precompile is basically that instead of doing this manually, we have the concept of like a basic block. A basic block means that you basically analyze this program at compile time, because you generate all of these like assembly code, and then you kind of dissect it by the like the branching instructions. Those can be like jump, branch, or things, whatever, just push a program to like a different instruction. You kind of dissect it like this. So this is a program, and then you just dissect it by these kind of instructions. And then you make this whole block like one, say like a custom instruction. And then in the CPU circuit, instead of having like one row for each of these like separate instructions, kind of similar to an auto precompile, a precompile without the auto part. For the auto precompile, this is done like automatically at compile time. You can just find like all of the basic blocks and like assign them each like a custom instruction. And then these gonna say like replace each row of the CPU circuit. So say that this has like 1, 2, 3, 4, 5, 6, 7, 8 rows in the CPU circuit. But with the 2 instructions, you have like a new CPU circuit that just has like 2 rows. It's like a CPU circuit new. And instead of having like all of these like each a separate chip for each of these instructions, they are like add, sub, load and store are the same one, and jump. So say like 4 chips here, you just have like the 2 chips, one for like instruction 1 and one for like instruction 2. And these have lots of the like optimization values to make the circuit faster. So first is that instead of like having a general purpose circuit where you have like the you have to like look up the program via the PC to like there's another like program circuit, read-only memory circuit, which is only of the fixed values. Instead of reading this to like to get like the value from the like read-only memory for the flags like such as like is add, is sub. So instead of doing all of this like during execution, you actually like within this custom circuit, you already know by compile time the order of all of these instructions. So you can already like have, say like, there's also like the same flags, like is add, is sub. So instead of like having these calculated during execution, you can already load them to like this custom circuit here that you have like the add, sub, load, add, something like this. So this reduces the need to like do this at execution. You can already do this at compile time. The other optimization for this is that given that you know these values like of the order of the instructions at compile time, you can like basically populate these constant values to the constraints of like your circuits here. And then you're gonna get a bunch of constraints. Like, so given you have the constant value already, when you like substitute them with the actual variables, you got things like 0 equal to 0, which can be like something like is add, maybe times like a minus b equals to 0. You know that this value at compile time for that row is like 0. So this kind of becomes like a constraint that isn't really needed anymore. So you can already remove this during compile time. And there's the last like advantage of not needing lots of the memory read and write stuffs. Like for example, within this chunk, you might have a bunch of like read and write, and you need to execute them like atomically for each row if you don't have this auto precompile thing. But once you have this, you can remove all of the intermediate memory stuff, and you just have the memory read and write at the start and the end of the custom instruction. So all of the other stuff becomes like intermediate for the memory accesses. So all of these are just maybe a very long overcap. Sorry about the timing stuff, but I'm gonna show a bit of benchmarking results for to give you a more concrete sense of like what we're able to achieve. 这个能开一下。这好像不行。重新插拔一下那个。这好小啊。 So this is the example people like the most because you almost always guarantee to write precompiles for this. So in the software version, for which we used like an existing crate called TinyKachak, it's basically like a bunch of Rust code, and these are basically the instruction you can like compile from that. So you see there's like roughly 120,000 CPU cycles, and these CPU cycle can be like calling the memory chip, the bitwise chip, the shift chip. Things like that. And these cycles basically refer to like the number of times it's being called. And then the manual Kachak is basically like the precompile, whatever like you write by hand. And you can see these also have a bunch of like these like submachine calls, but these are very optimized in general. And finally, you have the automatic Kachak, which is the auto precompile, for which you identify like the basic block, and then you generate like these custom instruction and then circuit that compile time like automatically. So these are also like more optimized than the software Kachak, but they are like not as optimized as the manual Kachak like in general. I mean, just for any manual circuit, the auto precompile is not going to work as well as them in general. But just to give you a better sense of what's going on here, so the CPU cycles get reduced because lots of the calls, for example, I mentioned earlier that you can eliminate the intermediate memory accesses. Those calls are getting reduced, like here. And then, because in the CPU circuit, so say if you have a is load, is sub, something like these. So in the CPU circuit, in the original software version, you're gonna have 7 rows in the CPU. But once you have the custom instruction, this becomes 1 row. So that's why you see the CPU cycles decrease a lot. But it definitely has the trade-off of the wechat cycles, which is basically this new instruction we make. So say this is basically wechat. Then you get calling this thing in either the compile, either the precompile or the So you call this custom circuit for the wechat 64 times in either the manual version or the automatic version. Yeah, and then these are some of the submission calls that are now easily, or in our case, we didn't really further make a precompile for them. So these stay roughly the same as the software version. But just to see the overall impact on the circuit, the common metric to use, at least in our case, was the number of cells. So basically multiply the cycles by the width, which is the number of columns. And we have the specific numbers here. So in the software version, basically you just multiply all of these matrices and add the cells together. This is the baseline value, roughly 20 million cells. But once we use the auto precompile, it's roughly a 2 times 56x improvement. But the manual version always gonna be superior, roughly 4 times improvement. But this is just an example because wechat is almost guaranteed to be written manually in circuit. But I think the thing with auto precompile is now that we just use it to precompile the wechat function, we can basically do this for any chunk in the program, and we can do this analysis on the fly at compile time. And this is actually very advantageous because there can be lots of long chunks in the given program, whatever program, but people don't typically recognize that that chunk has say a wechat function or something. But with this auto precompile, we can identify whatever number of basic blocks we want, and then do the precompile on the fly. And that gave you the improvement, which is not going to be as good as the manual stuff, but still going to be much better than if you were just to execute each of these instructions separately. So that's the main advantage of doing this kind of auto precompile stuff. And then there's going to be different results. This is another example. It's not the wechat anymore, but the wechat benchmark I just showed only has 1 basic block accelerated. But you can do this actually for however many basic block you want. So say you have a program with 700 instructions, basically 700 lines in the CPU, and then this has 100 basic blocks. And then you can basically just choose the top, say top 5 most expensive, expensive basic blocks. So say the first one has maybe 30 rows, 30 instructions, I mean. The second has 25. You can do this analysis at compile time and then select the top 2 or top whatever and do this kind of optimization. And these are the results in general. So you can see that the more circuits, basically the more basic blocks you do the auto precompile for, the more time saving you're gonna get. And these are I think here. Yeah. So I have a 3x improvement for the 1 acceleration, 5.6x, 6.2, 6.3. But again, this is just for a specific example, but just to show the idea that you have, the more you accelerate, the more it's going to get faster. But definitely with the cost of you're going to do more compile time analysis. So in practice, the kind of time saving is going to get flattened out at the right-hand side. And then you need to balance that with the added compile time. So you're not going to necessarily choose the most number of circuits to accelerate for, but maybe you also need to add the row for like compile time, and this is going to increase as well. And you're going to find like maybe the sweet spot of the number of circuits to accelerate in general. And then there's another thing I've been working on this week, which is basically helping select the basic block to accelerate. So there are actually two methods of doing that. One is compile time only. The other also requires some like runtime analysis. So for the compile time only, as whatever I just talked about earlier, basically you have this program, you have all of these basic blocks, you have the number of instructions in them, you sort them by descending order, like 30 instructions, 25, 17, like 2, 1, 1, 1. You just use this as the cost function to determine like how expensive this like precompile this block is, and then do that for like the top couple of blocks. And this is compile time only, because if you have the program, you can do this analysis. But the other maybe more involved kind of optimization is runtime, for which you actually need to execute the program. And then you have this notion of length. Length is basically the same metric as this, basically the number of instructions here, and then you multiply that by the frequency it's being executed. Because in the program, like this, so say you have like 3 basic blocks, so these can get ranked like this, but in the actual execution, you never know like if these are all going to be called or the number of times it might be called, because there might be like loops and jumps around it. So say that this is like 30 instructions, but this only gets called like 1 time. This is 25, but it gets called like 3 times. This is like 100 instructions, but it never gets called in the actual execution. And then you can just multiply them to get this like cost function during runtime. And then you can sort this by their cost in the descending order. And then instead of like doing this, you can like use this as the cost function to determine like the most expensive thing to optimize for. So that's roughly the other idea I've been implementing this week. And here is basically corresponding to this idea of the cost function. So first, during the execution, I calculate, I have a PC trace. I have a program trace here. So these are like the PC counter. This is like the whole check function. You see these are like the corresponding to like which line in the program is being executed. Basically, that's an execution trace, but just with the PC. And then I do like a tally of the occurrences for these program counters. So you'll see I have this. This is basically a printout of the map. So the PC index, 90 got executed 32 times, and these got 28 times. And then there's a bunch of like long tail stuff, gets only 1 execution per PC. And after printing this whole map, I like have this data for the basic blocks. The start index is basically it's too small. Yeah, the start index is basically like the PC of like the start instruction of this block. And then you have like the length, which is basically the like number of instructions here. And then you have the frequency, which is the number of time is executed during the like pre-execution run. And then you multiply them to get the cost, and then sort it by descending order. And then there's like an argument in the command line you can just input to say like just accelerate the top 3 blocks for this cost function. And that's something we do for the acceleration. Yeah, so that's roughly my presentation. Thank you.